episode of Progress, Potential, and Possibilities, discussions with fascinating people designing a better tomorrow for all of us. I'm your host, Ira Pastor.
Okay, wonderful. Welcome everybody again to another episode of our show. I'm going to start off today with some very interesting figures to lay the groundwork for our discussion. So around the world, there are an estimated 1,500 potentially active volcanoes, aside from the ones that are beneath the ocean floor. And it is estimated about 500 of those 1,500 have erupted within historical time. The last supervolcano, of which there are still 20 on the planet, erupted around 26,000 years ago in New Zealand, and the estimated force to achieve that eruption was estimated to be around the equivalent of 100,000 Hiroshima nuclear bombs. So quite a bit of energy generated. We're honored today to be joined by Dr. Graham Ryan, who is director at the Montserrat Volcano Observatory in Montserrat in the West Indies. Dr. Ryan has 17 years of experience in volcanology and geothermal geophysics, and he uses his skills to better understand the nature and behavior of magmatic systems and fluid flow through geothermal systems. His current research interests include ground deformation associated with volcanic systems of the Eastern Caribbean, and also joint interpretation and inversion to determine the architecture of geothermal and magnetic systems within the region. Dr. Ryan has a master's in physics from the University of Manchester, a PhD in volcanology from Lancaster University, and has published over 20 articles and book chapters in a variety of peer-reviewed international publications. In addition to his work at the Montserrat Volcano Observatory, he also spent 6 years at the University of Auckland in New Zealand, studying a wide range of topics, including the fluid flow pathways in geothermal systems, and with a particular eye to targeting geothermal wells for energy production. And while he was based in New Zealand, he traveled around the world in a variety of countries, studying volcanoes, including Montserrat, but also Rwanda, Chile, the United States. And he's also developed expertise in electromagnetic induction, particularly magnetometallic techniques useful for imaging systems deep within the Earth's crust. So a lot of very exciting topics to talk about today. Dr. Ryan, thank you for taking the time out of your schedule to come on the show today.
Yeah, thank you, Ira. Thanks for that introduction. I also learned lots of things about volcanoes just now. How many there are and all this. I tend to be quite myopic and like just focus on the one that I'm on.
That's okay. I figured I try to get up to speed a little bit.
Yeah.
So, Dr. Ryan, typically we start the show off by handing our guests the floor for a little bit just to talk about themselves. If you could just take a little time to introduce yourself, talk about sort of where you grew up, how you developed your interest in science, in physics and geophysics, and obviously volcanology, and a little bit of your path to date. I think that'd be a great way to sort of lay the groundwork for everything we're going to be discussing.
Yeah, well, I've kind of led an itinerant life, really. I was born in the United Kingdom, but I came to Montserrat when I was about 7 years old. So in terms of interest in science, I think since I was a pretty small kid, I've just been interested in science. I think maybe from television, like characters like Spock and the professor on Gilligan's Island and all these kinds of people who had this kind of esoteric knowledge and were able to figure things out and make things. I thought that was really exciting. I kind of wanted to be able to do that. It seemed like the kind of closest thing to real magic. So that's, I think, yeah, ever since I was a little kid, I was just kind of interested in kind of trying to gain that kind of knowledge. And so moved to Montserrat and when I was 7. And then when I was 16, I went back to the UK and did my A-level exams, like maths, physics, chemistry, and then went to the University of Manchester, where I did a degree in physics. Was actually physics with technological physics. It was like physics, some electronics, some computer programming. And so that was my kind of first idea. I didn't really have a full plan of what I was going to do. I really was just following my interest. So I was really interested in physics, and so I was do that and figure out the rest later on. But when I was midway through my degree, so I started my degree in 1993, and in 1995, the Soufriere Hills volcano in Montserrat started erupting. So I came home in the summer of '96 to Montserrat, and it just seemed, there was a lot of interesting stuff going on at the Volcano Observatory. So I obviously, I was midway through physics, and they were, using lots of interesting instruments and stuff. So I went to the Volcano Observatory and volunteered to kind of work there. And so I did that during the summer in '96, and that's kind of where I got interested in volcanology. So it was a really exciting time. The moment was the beginning of the eruption, and it was still kind of establishing the Volcano Observatory and establishing the monitoring, and there wasn't a fixed complement of staff as like we have now. There would be like volcanology professors would come in for like a month or two, and they'd bring their PhD students and kind of work with local staff to do the monitoring. So there's always just an influx of new people and new students. So it was really kind of an exciting time to do lots of kind of young PhD students as a volcano erupting, and you're doing lots of interesting stuff. So I think that's kind of where I got bitten by the bug then, and decided that I wanted to do a PhD in volcanology kind of after that. So I came back, so the next year, '97, I came back and did the same thing again. And then I graduated in '97, and I started a PhD in 1998 at Lancaster University. So there, I'd kind of switched gears a bit, because I've been involved in kind of active monitoring, well, kind of adjacent and kind of helping out with that and this. And then when at Lancaster, the project I was doing was more experimental. So we kind of built a kind of a volcano in the lab, and the original idea was to look at fragmentation, which is, what happens when a volcano erupts. The magma is coming up, the bubbles start coming out of the magma, and it eventually kind of rips itself apart, and you get these eruptions that produce pumice, which is volcanic rocks that are full of bubbles. And so the initial plan was to look at that fragmentation process using something called gum rosin, which is what I think they use that for violin bows. They kind of rub that on violin bows for some reason. So we'd kind of make a fluid mixture with the gum rosin and diethyl ether, and then rapidly decompress that, and then that would create this bubbly flow that would then fragment and put pressure transducers and so forth to kind of study that process. But during the experiments, I became more interested in what was happening after the fragmentation. So initially, like, the experiment was over after like 3 seconds, and I just left the stuff running in the lab kind of overnight for, I don't know, whatever reason. And I came back the next day, and there was these really interesting signals in the pressure transducers that I wasn't expecting. It was kind of like a sawtooth signal, so the pressure would rise and then drop and rise and then drop, and it just kept kind of going on and on. I was like, oh, that's really interesting, and it was something that I'd seen in Montserrat, where there was these things called tilt cycles. So a tilt meter just measures kind of how the inclination is changing. So as magma comes into a system, it causes the ground to kind of swell up. So the various ground deformation techniques that you look at to see how the ground is responding to influx of magma. And one of those is a tilt meter. So it's very, you're looking at micro degrees of change. So early in the eruption, there's this tilt meter that was quite close into the volcano, and it was producing these tilt cycles every few hours. It would kind of go up and come down, and then at one point it turned out these tilt cycles were coincident with explosions. There was a period of time when we were getting explosions every few hours, and it would coincide with these tilt cycles. The tilt would increase, and then boom, it would explode and then drop. So that was why I became very interested in these tilt cycles. Oh, was this related to what I'd seen then? So kind of my research kind of went down that path of looking at these tilt cycles and what was causing them, and how they might be related to explosive activity. So I did that, and so did my PhD, and then I actually still wasn't. I still didn't really have a plan. I was still just following, what's the next interesting thing to do. Mm-hmm. So it's kind of, I did the PhD. Oh, this is really interesting. This is cool. Let's do that. I hadn't really said, oh, I'll go and work at the Volcano Observatory afterwards. So I was like, I don't know what I'm going to do. But I came back to Montserrat, and the director at the time, then Jill Jolly, she offered me a job, and I was like, okay, yeah, I'll do that. So I worked here at the Volcano Observatory. That was, when did I start? That was 2003. I started at the Volcano Observatory here. I did a variety of different jobs. We had kind of smaller staff, so I did the ground deformation monitoring. So we have a series. The backbone of that is a series of very sensitive, continuous GPS stations that we have around the volcano, various places. And so, kind of normal GPS in your car, gets you to within a few meters, sure, of where you actually are. But these GPS will get you to, a centimeter or less. So you can see what is, how this deformation is evolving. And so Montserrat is a very interesting deformation signal. So the eruption here is episodic, and so we have started in '95 and technically still ongoing in 2020. And in that period, there have been 5 phases of eruptive activity. So you'd have, an eruption with magma coming out and explosions and pyroclastic flows, which are avalanches of hot rock and ash and things like that. And that would go on for a couple of years, and then it would stop for like a year or two, and there'd be no magma coming out, and then it would start again, and you have a few years of activity, and it stops, and so on. So of these stops and starts, and when you look at the ground deformation during the times when there's no magma coming out, the ground kind of swells up and swells up and swells up, and then when it starts erupting, it subsides like that. And so the idea, kind of a standard model, is that magma is coming into the magma chamber that's feeding the eruption and causing the ground to kind of swell out as to accommodate this bigger and bigger magma chamber. And then when it erupts, the magma is coming out, and that balloon underneath, think about it, is kind of emptying out, and the balloon is collapsing and comes down. So I was doing that. Another thing that we look at is gas fluxes. The major flux that we measure is sulfur dioxide. So that's one of the major volcanic gases. I mean, actually, the biggest one is water vapor, but that's kind of harder to measure because there's water vapor in the atmosphere already. So we look at sulfur dioxide coming out, and so it was an interesting time. So they were just pioneering these scanning UV spectrometers. So they scan through the plume. So over about 6 minutes or so, they'll scan through, and you can then reconstruct how much sulfur dioxide is coming out of the whole volcano by kind of scanning through it every 6 minutes. And so you can get continuous sulfur dioxide fluxes as they come out. And also, obviously, one of the things that you need to keep track of is how much magma is coming out. So we need to measure the volume of the dome. So when it's extruding, obviously the dome is getting bigger and bigger and bigger, and we want to see what that rate is, because if it's coming out more quickly, that might mean that you might be more prone to explosive activity and so on. So we do that. So actually developed like a kind of in-house photogrammetry method, kind of a hodgepodge. It's not really true photogrammetry. This is back in the kind of mid-2000s. Now we have really lots of awesome software, and things like Agisoft. You can take pictures of things and create nice DEMs, but I didn't have that back in the day, so I had to kind of make my own kind of thing. So I'd get as close to the volcano as I could, take a picture at one spot, and then go somewhere else, take another picture at another spot, and then kind of, I would by eye say, okay, that boulder is in this picture, that boulder is in that picture, and kind of reconstruct points on the dome, and then kind of model the volcano, and then calculate the volumes and stuff like that. So that was one of the other things I was doing. So that was pretty interesting, and there was a lot of activity in that time. It was it was quite an interesting time. And then in 2008, I guess I was kind of getting itchy feet, and we had a big project that we were part of called Sea Calypso, which was a P-wave tomography survey for the whole island. So we went around in a ship for several days, towing what's called an air gun, which produces blasts every minute or so as you go around the island. And then we had maybe a couple of hundred seismometers on the island, which are recording these blasts. And so the idea is that the seismic waves go down under the earth and then back up to the seismometers on the island. And by looking at the travel times, how long the seismic waves take to go from the air gun to the seismometer on the island, you can calculate what the P-wave velocity must be underneath the island.
Okay.
And so you're looking at seismic velocities, average might be something like 6 kilometers a second, 7 kilometers a second, and in some parts it might be 6, some parts it might be 8, and so you're looking at these variations in P wave velocity under the island. The idea was we'll be able to find the magma chamber using this and make a picture of it, because the P wave velocity should be different in the magma. Could be slower if it's very bubbly. That might cause it to be quite slow. If it were quite dense, it might even be faster than kind of fractured rock around it.
Mm-hmm.
So it's kind of find that. But it turned out that that didn't quite work as neatly as possible as was hoped, because the waves were actually kind of bending back up. So like the seismic waves, leave the air gun and then they go down and then go through the subsurface, and then they kind of bend back up because of the change in velocity causes this kind of bending, kind of refraction of the seismic waves. And what was happening was they were kind of bending back up before they got deep enough to see the magma chamber.
Mm-hmm.
And so quite work as neatly as possible. We're still able to make some inferences using like reflected waves and stuff like that. So, but it's still got some really nice data down to 4 or 5 kilometers. Where we think the magma chamber is like below about 6 kilometers. But during that project, there were a number of different universities involved in that, and one was Duke University.
Sure.
And there was a professor, Peter Mallon. He was just about to move to New Zealand to start a new research institute there. And so while he was there in Montserrat, he offered me a job in New Zealand. So, I thought, oh, that sounds exciting, and go and do something else. And so I went to New Zealand in 2008 and got into, so there, they were mainly interested in geothermal systems. Mm-hmm. And kind of mapping geothermal systems and looking at that. So that's what I did for the next few years. I was there between 2008 2014, and as I said, I was mainly using magnetotellurics, okay. Which is a method for measuring and modeling subsurface resistivity. So resistivity is how easily an electric current can flow through things. So it's like, it's related to resistance. So you kind of have high resistance materials like plastics that don't conduct electricity very easily, and obviously things like metals are very high conductivity or low resistivity, and they conduct very well. So what you're doing is you're kind of measuring the resistivity in the subsurface to try and infer something about what's going on. And so for geothermal systems, what happens is where you have high temperatures, kind of over 70 to 90 degrees Celsius in subsurface with fluid, it basically kind of rots the rock and turns it into clay. So like the rock turns into these clays, and the clays are very conductive, whereas pristine rock is not conductive at all. It's very low resistivity. So what you see when you have a geothermal system, you'll have this very low resistivity cap, which is called a clay cap, and it shows up very clearly and can tell you, okay, how, that you have a geothermal system there, how deep it is, and what the extent of it is. So I spent a lot of time doing that kind of work in different places. Like I said, I did quite a lot in New Zealand. I did some in the Western US in Nevada. We did quite a big survey in Rwanda. They were so trying to see if they had a geothermal resource there. And actually, almost coincidentally, in Montserrat, they started to, at the time that I left, they got interested in geothermal energy. And so it just turned out that we kind of won the contract to do the geophysical exploration in Montserrat. So I ended up coming from New Zealand back to Montserrat to do the magnetotelluric survey there. So I did that, and that was 2009. So after 2008, was back in 2009, and I ended up almost every year I was in New Zealand, I'd come back to Montserrat to do various work for the geothermal stuff. So there was kind of that kind of link that just kind of kept kind of pulling me back. But just without, it wasn't any real plan there. That's just how it played out. And so yeah, so I did that, and then 2014, so I was at the University of Auckland, and it was a research institute, but it was kind of novel structure where we were doing some commercial work as well as research, and the kind of idea was to try and make the commercial stuff fund the research. And then, like in 2014, the institute got spun out into a kind of more purely commercial operation. And so I was like, well, I think I really like the research side of things more than the commercial side of things. So I decided to, look for a new job at that point. And at that point, the University of the West Indies, which there's 3 major campuses. We have one in Jamaica at Mona, one in Barbados at Cave Hill, and one in Trinidad at St. Augustine. And so the Seismic Research Center was advertising for a geophysicist, who actually was actually a geochemist, actually, they were advertising for. But I put in an application, and I was successful. So I went to Trinidad, so I was, kind of back in the region again. So yeah, Trinidad is quite just adjacent to Venezuela. It's about 7 kilometers from Venezuela. Whereas Montserrat is a bit more northerly. But the Seismic Research Center has responsibility for monitoring earthquakes, volcanoes, and tsunamis in the English-speaking Caribbean.
Okay. And
it also had the contract to manage the Montserrat Volcano Observatory. So when I came back, I was in charge of looking at ground deformation across the region, but because we also worked with, we were in charge of managing the Montserrat Volcano Observatory. When a member of staff would go on holiday, or something they needed cover, then I would go and kind of fill in. So kind of came back to Montserrat again in that kind of way. So that was it was good. So involved in various things. I'd come back to Montserrat and do some things from time to time, and kind of stay involved with the geothermal project. And then when was it? 2019, the post for director became vacant, and so I applied and was successful with that. So now I'm back in Montserrat as the director of the Volcano Observatory here. So I think that kind of brings us up to the present day.
Absolutely. A wonderful journey. And
yeah.
back to Montserrat, but hey, there's something, there's something behind it
Yeah.
all.
Yeah.
Yeah, it's a fascinating journey. One of the things that you mentioned is this topic of magnetotellurics, which you've been very actively involved in terms of looking at these geomagnetic and geoelectric fields and so forth. What if looking at other technologies that from your perspective as a volcanologist and once again I'm talking I shouldn't be talking out of purpose here just because I have no experience in this area, but we talk about technologies like artificial intelligence and machine learning and other things obviously for predicting in the future. We talked a little bit about this with hurricanes. I'm up here on the east coast of the United States, and I see more hurricanes than anything, earthquakes or volcanoes, of course. Any interesting tools along these lines, or other things that you're developing, obviously not confidential, that are going to be useful for shortening that or expanding the amount of time when something dangerous is going to happen in one of these locations?
It's interesting. I mean, obviously, lots of people are doing research in various areas, including AI. I'm not too au fait with exactly what's going on in that area, but there's no kind of killer kind of application that's come out of that yet. And like one of the problems, it could be, I think for things like AI, you need to have a lot of training data.
Sure.
And in volcanology, I think getting that amount of data can be quite difficult, and each volcano is kind of different, so it's kind of probably a harder problem than in some other domains where the problem is kind of more constrained, and you can really have a ton of very kind of well-behaved data that you can kind of attack. So I think that's probably why it hasn't borne fruit yet. Not to say that it won't. In terms of machine learning, I mean, obviously machine learning is a very broad kind of area, and so actually my PhD student has just had like a manuscript accepted where we're kind of using machine learning for the Montserrat geothermal system. So as I said, it started in 2009, and I've just kind of been noodling away trying to kind of get a better understanding of the system here. And so one of the things that Racine has been looking at is using fuzzy clustering to create a subsurface model of the geothermal system. So we talked briefly, and so it's a clay cap. And so for Montserrat's really great because it's the focus of a lot of research. And so there are a lot of different data sets that you have access to that in different places you might not. And so like here we had the sea calypsos, we have this P-wave tomography, which although it didn't quite work as hoped finding the magma chamber, the depth range is perfect for looking at the geothermal system. So the geothermal system. So here we've drilled 3 wells, and to depths of up to 2.8 kilometers. And the model is pretty good down to 3-4 kilometers for the P-wave. So we have really nice information from that. We have nice information from the magnetotelluric study that I did, which also gives us some stuff. And we had Stephanie Houtman did some gravity surveys on the island. So you're looking at kind of microgravity and like looking at minute differences in gravity from place to place. which tell you something about the structure of the subsurface and, like, you know, how the density is varying. So we have these three very nice three-dimensional models, one of how density is varying in the subsurface, one of how resistivity is varying in the subsurface, and one of how P-wave velocity is varying in the subsurface. So in theory, for each point in the subsurface, we have these three different values. And so using the clustering, you can pick out, okay, oh, this area, you can pick out different clusters of properties that go together, and then we can interpret them. So we've interpreted, okay, this is where the clay cap is. It's got a very low resistivity, it's got a low P-wave velocity, and kind of lowish density. And, you know, this is the kind of unaltered rock. It's got kind of a low P-wave velocity, but very high resistivity, and like a medium kind of density. So using that kind of idea, we can like we can take the data and then turn it into an interpretation. This is the clay cap. This is where the geothermal reservoir is. Mm-hmm. This is where you have unaltered rock sitting on top of it. This is where you kind of have the dense basement below the reservoir. And so we've been using clustering to kind of squeeze more interpretation out of the data. So that's one kind of simple application we kind of utilize.
Mm-hmm. When it comes to the region in CARICOM, I think you have a volcano. I think Dominica, St. Vincent. Yeah. Once again, amateurish question here, but because I only see hurricanes.
Yeah, well, yeah, you're not an expert. It's fine.
But what is the volcanology community like, in the sense that do you plan things sort of as a group, and then sort of are there things that you study in terms of volcano clusters, let's say, in a specific area, or is it solely, we're only going to focus on? I'm just trying to think of it, because when you think about hurricanes, right? In the Atlantic, they start off the coast of Africa and they swing to the South Atlantic. And are volcanoes connected intricately in similar context? And could you learn something from what's happening in Montserrat with what's going to happen in St. Vincent and so forth?
Yeah. So I mean, each volcano is different. But so yeah, there are going to be differences, but you can learn lessons from one volcano and kind of see them in others, and there are different kinds of volcanoes.
Okay.
So and they occur in different settings. So here, all of the volcanoes in the Lesser Antilles are there because of subduction zone volcanism. Okay. So you have the Atlantic plate, this is the Caribbean plate, and the Atlantic plate here, and this Atlantic plate is subducting as plate tectonics, and it kind of keeps moving and it goes down, down, down. And so as that plate goes down, broadly, water gets kind of squeezed out of this plate because it's been sitting under the ocean for millions of years. There's lots of water-rich sediments in it, and it goes down, and this water comes out and kind of trickles up into the mantle, and that water lowers the melting temperature of the mantle and essentially melts the mantle, and then this magma then kind of starts to buoyantly ascend, and kind of where it makes its way to the surface, you have a volcano. And that's the process that is responsible for all of the volcanoes in the Lesser Antilles.
Okay.
So that's you know, and they have a particular kind of chemistry. So broadly, so like Hawaiian volcanoes are completely different.
Okay.
Well, I mean, they're still volcanoes,
Mm-hmm.
but so I mean, I won't go too much detail, but those are hotspot volcanoes. So there you have a plume that's coming directly from the mantle, like a convection plume that's coming straight up in Hawaii and coming straight up and then kind of like punching a hole through the crust. And as the plate moves along, kind of punches up in a new place and punches up in a new place. And that's why you have a chain of Hawaiian islands. That's the plate moving along and this hot plume is coming through. And so that kind of magma is very relatively low in silica. So that's, for me, I'm not a geochemist, so I've done more physics, so I kind of think in very broad brush terms.
Mm-hmm.
So in Hawaii, you have very low silica, and the lava and the lava that comes out is very runny, and that's why you have these nice lava flows and fire fountains of lava coming up and creating these fire fountains. So the kinds of behaviors that you see are controlled by the viscosity of the lava, which is controlled by the chemistry of the lava, as in it has not as much silica. So silica is kind of a polymerizing agent, so it tends to kind of bind things up. And in the Caribbean, where you have the subduction zone volcanism, that produces a much higher silica concentration in the lava. So it's very sticky when it comes out. So you do not have generally lava flows. This stuff comes out and you have this dome forming eruptions, and you don't get lava flows, you don't get fire fountains, you get Volcanian explosions, where the thing just explodes and creates pumice,
Mm-hmm.
and comes down. You get pyroclastic flows, where the dome, well, there's two different ways of getting pyroclastic flows. Classic ways, the dome builds up,
Mm-hmm.
and then a piece of it breaks off and creates an avalanche of rock and ash at 600 degrees that kind of then races down the side of the volcano. But you can also get a pyroclastic flow when you have an explosion that produces a big eruption column that goes up, and then what can happen sometimes, it doesn't become buoyant, it just collapses back down again. And you get a column collapse pyroclastic flow. So this thing goes up and then drops back down, and you get pyroclastic flow of pumice and hot ash that then goes off, races off in all different directions. And so I'm saying all that to say that different kinds of volcanoes have different hazards associated with them and different modes of expression. So you can, if you study what's happening at Montserrat and look at the pyroclastic flows, that'll tell you about what's going to happen with pyroclastic flows on another similar volcano. Mm-hmm. But you're not going to see pyroclastic flows and these kinds of explosions in Hawaii, because it's a different kind of system. So there's still lessons to be learned, but different. And so yes, there are similar things about volcanoes in the region and in other similar settings around the world. So other subduction zone volcanic arcs in different parts of the world, and so we can learn things from them. And so regionally, the Seismic Research Center studies all of the volcanoes in the region. So we kind of coordinate our kind of research around, looking at all these volcanoes and seeing what lessons we can learn and what kind of broad trends we can see. And then there are lots of people doing research around the world, and what, they might be interested in one specific island. So we can try and collate all of that information and kind of build a broader picture of what's happening from lots of different strands of research that are coming in from different places. So, well, anyway, if you have more questions, you can ask.
No. I appreciate it. I apologize asking for the lecture, but it's very interesting, and bringing us to speed. I appreciate that you spent time on that. Future visions. Obviously, you're in a range of fascinating research. You like the research side of things. You mentioned a little bit about the geothermal energy production. Other interesting things looking out the next 5-10 years, whether it's for how new technologies are capturing energy, or chemical products from volcanoes. Any interesting? I know you don't say on the commercial side much, but anything coming down the pike that's like, wow, that'd be pretty cool if we could harness this or that.
So I said, it's more, I guess, in terms of what the big questions are. Whether I'm not sure, if the answers are there yet. But in terms of geothermal energy, the big problem you have is permeability.
Okay.
Which is how well fluid flows through a kind of region. And so to successfully exploit a geothermal system, you need high temperatures, you need to have fluid, and you need to have good permeability. So you drill a well into this region and the fluid flows into it and up the well, and you can exploit the energy from this high temperature fluid. And so one of the big problems with geothermal development is the high risk involved in drilling a well, because they're very expensive, several $1 million for each well.
Okay.
And the returns for geothermal are not as high as in the fossil fuel industry. So the risk to benefit ratio kind of makes it more difficult for people to kind of financially justify. Okay, we'll just drill 10 wells and we'll see what we get, because that's maybe $60 million.
Okay.
And you're not sure what you're going to have. So one of the areas of research that I'm interested in is how do we find these high permeability regions in the subsurface, and so that we can target the wells to these high permeability regions. And so that's kind of the part of a long kind of research program that we're working on. So it's things like looking at multiple data sets together to kind of refine the subsurface interpretation. Looking at the subsurface temperature distribution, and then using that to constrain like how must the fluid be flowing in the sub. Right. Okay, what were we talking about?
You were just telling us about the future. Your future plans.
I was talking about subsurface. Yeah, so if you look at the subsurface temperature, then you can infer how must the fluid be flowing in the subsurface to give you that temperature distribution. And if you know where the fluid is flowing, then the fluid is going to flow where you have high permeability, because the fluid's going to want to go where it can go. And so by using these different methodologies, you can hopefully build up a subsurface permeability structure that you can then use to have higher confidence when you drill a well that it's going to be productive. And so that would be quite useful in terms of managing the financial risk and make it more kind of financially viable. So, so like a normal well maybe has like a 25% probability of being productive. So if you can get that to 50% or 75%, then that'll encourage more take-up of this energy source, which in the region here we have really high energy costs because we generally use fossil fuels, and so we have some of the highest energy costs globally. It's only much higher than the US and so on. So that kind of puts a brake on kind of how much development you can have if your energy is very costly.
Sure.
So, but as you pointed out, there's lots of volcanoes in the region. There's lots of geothermal resource, and so if we can utilize that can be really beneficial. So that's kind of what I've been looking at there. In terms of volcanoes, volcanology is a really, in many ways, a very young science. I'm not great on my history of science, but my interpretation is really kind of like in the 70s and 80s when volcanology started to become more of a quantitative rather than purely descriptive kind of science. So I think it's Professor George Walker in the 70s. He kind of started to use more quantitative methods and kind of bringing in more physics, mathematics to describe processes and kind of pin things down a bit more. And so it's really quite young, and we have a lot of understanding about the general processes, but a lot of the very important questions as to, is this volcano going to erupt? How big is this volcanic eruption going to be? How long is it going to go on for? Even like a seemingly trivial question like, is this volcanic eruption over? These are all questions that don't have really solid answers to them. So those are the kind of questions that we're looking at. So for example, is this eruption over? So I said this is here in Montserrat, it's an episodic eruption. It started in 95 and we've had 5 phases of activity. Now the last phase of activity was in 2010. That was phase 5 essentially. And it's 2020 now. So the obvious question is this eruption finished? Did it finish 10 years ago? And at the moment we don't think it is. But pinning down exactly, unequivocally, the answer to that question is actually a difficult question. So we have 3 main kind of monitoring techniques, and we have a standard model that we use in Montserrat, kind of how we interpret that monitoring data. And that's ground deformation, the sulfur dioxide gas flux, and seismic activity. We talk much about seismic activity, but actually that's the most important thing. It's because, I guess it's because I'm not a seismologist that I didn't talk about it that much, but it's probably like one of the best tools for volcano monitoring is seismometers. So we, as I said earlier, during a pause, what we've seen is that the volcano, I'm not sure, I've actually got a picture of it here. High tech. I can't, let's see what's going on there. Okay,
It's got a lot
So
of nice
that,
colors on it.
yeah. So this is what we call our mega plot,
Okay.
which shows the main monitoring data. But we're just going to focus on those lines.
Okay.
It starts off in red and then turns blue at the end there.
Yep.
And so what you see is during the pause, it's going up. During activity, it goes down. And at the moment, it's still going up. That blue line is still increasing.
Mm-hmm.
And so our standard model says that means that magma is still coming into the magma chamber.
Mm-hmm. Mm-hmm.
And that's what's causing this thing to keep swelling up. So if that's the case, then it means that the magmatic system is still active.
Got it.
And we still have a decent probability of having more activity in the future. And this is just a very long pause.
Got it.
Similarly, with the gas flux, like none of the other islands produce significant quantities of sulfur dioxide. And they all have volcanic systems, whereas we producing about 200 to 300 tons per day at the moment of sulfur dioxide, which is it's a big excess of sulfur dioxide.
Sure.
And so in our standard model, we think that the magma that's coming from very deep, it's got lots of sulfur in it, and when it comes into the shallow magma chamber, it gives off its sulfur dioxide, and that's why we see this excess sulfur dioxide. So again, that means we still got stuff coming in. It can go off again in the future. And then we have seismicity, different kinds of earthquakes that we look at. Just going to quick run down. So volcanotectonic, which are just similar to the kinds of earthquakes that people know about, but just on a very small scale and produced by the volcanic system. And we have long period earthquakes, which are these low frequency earthquakes, which tend to be associated with fluid flow and gas flow in the conduit. And hybrid earthquakes, which are a mix. If you look at them, they look partly like volcanotectonic earthquakes and partly like long period earthquakes. So they start off looking quite like a VT or volcanotectonic earthquake, and then they end looking like a long period earthquake. And we tend to see those when things are really, the magma's really moving in the conduit, and it's causing kind of little ruptures in the conduit wall and gas flowing through those ruptures. So, so we look at these kinds of earthquakes. At the moment, we have very low. Are you still there, Ira? Okay.
I'm here. Can you?
You're frozen. Yeah,
okay.
Your video was frozen just now. So we're seeing very low levels of seismicity at the moment, but we're still seeing these volcanotectonic earthquakes, and occasionally we get what we call in-house, we call them volcanotectonic strings, or VT strings, which are small swarms of earthquakes. So you'll see, maybe a few dozen earthquakes happening over a couple of hours. And those, happen periodically. So we're still seeing some seismicity, we're seeing this deformation, we're seeing this gas. So we're like, okay, we think it's not over, but it's been 10 years and nothing has happened. And so at the moment, we're looking at different explanations. Are there any alternative ways of looking at this? So one idea that's being kind of hotly debated at the moment and is still in its very early stages is the idea that the rheology of the crust might be such that you see a delayed response. So it's called viscoelasticity.
Okay.
So if you played with oobleck, cornstarch stuff.
Sure.
That's a kind of viscoelastic kind of material. So on short time scales, it behaves elastically, and then on long-term time scales, it behaves in a kind of viscous fashion. And so the idea is that you can introduce a pressure source in the subsurface, and the ground kind of responds to it, and then over a long period of time, it just kind of creeps out. Even though the pressure hasn't changed, it keeps creeping, and that could be an explanation for what you see. But as I said, it's very early days for that interpretation. Still, we need to better understand, what is the rheology of the crust. It's also very dependent on what the thermal structure is in the crust. You need to have relatively high temperatures, kind of unusually high temperatures to see that, and it would have to be across the whole island. And the different kinds of rheological models. It gets into lots of subtleties as to whether this is a viable explanation or not. So those are the kinds of things that we're kind of looking at to kind of better understand, these extremely simple, naive questions of like, simple as, is this eruption over?
Yeah.
So there's a lot of work to be done on those, and I think there's no real silver bullet on the horizon. I mean, at the moment, so we have the main tool that we use for like looking at these big questions is something called expert elicitation.
Okay.
Which we have every year we will have some of the top scientists from around the world come and like kind of all look at the data together, and then people will say, what's the probability that this eruption is going to start again in 12 months? And people will say, everybody would have their own different percentages and range of confidence, and all of that goes into a pot, and the answer comes out that way. So it's, it's kind of strange. So we can be very, we can do lots of very sophisticated science in certain areas.
Sure.
But then in other areas, you don't, the tools to get those answers are just not developed enough, and we have to kind of use these other kinds of tools, which rely on people's experience and intuition and things like that. So it's kind of bizarre.
Well, I just you stimulated a thought for a second there, and actually, I as you'll know, when they watch this show, I usually give the bio of my guests to my children and see if they come up with anything interesting. First of all, when I told them I was talking to you, they lost their mind. They thought it was the coolest thing in the world. But obviously, they watch documentaries and so forth nowadays, and the topic came up about these super volcanoes. When you get your thought leader group together, or whenever you're sitting around just thinking about other stuff, does the topic of supervolcano and sort of obviously this question, hey, are we over, or are we due something yet, of any concern to the volcanology community in any way that any of us normal people should be concerned?
Yeah, well, I mean, like I said, we generally, it's a very focused meeting, and we're like all, very focused on what we're doing. So we don't generally talk about supervolcanoes, but it's just one of those things that's out there, which can take us all out, and probably
the question.
probably will happen at some point in time, but like the probability that's going to happen in the next 100 years is kind of manageably small enough that I can get to sleep at night.
Okay.
So
I'll let them know.
but it's one of those things that's out there, like being hit by an asteroid or something that you have minimal control over, but the probabilities is small enough that you're not kind of, existentially kind of petrified.
Gotcha. All right. I'll assuage their concerns. I appreciate that. Dr. Wright, coming back to you, we typically ask a wrap-up question about the important mentors and influencers that you've had throughout your career. You've mentioned a couple as you've been discussing what you've been up to. At this point, any other individuals, whether they be professors or colleagues, family members that you might want to shout out to now, mention that have been really instrumental as you've made this amazing journey from Montserrat around the world and back? You're doing?
Oh dear. Well, yeah, I'll probably forget a whole bunch of people. But yeah, I mean, I said, like, my family has always been great. They've never kind of really put any pressure on me to, do certain things. I've just been kind of always just felt free to just follow whatever I found interesting. And luckily that's kind of worked out for me so far. And so I think that's been really, really beneficial. In terms of other mentors, so when I was at secondary school, and we had this subject called electricity and electronics, and it turned out to be kind of a very formative experience, because I don't think you would get away with these methods now. It was pretty kind of a bit brutal sometimes. It was because a teacher called Mr. Jarvis, but he kind of really, compared to the other subjects, which I kind of found, reasonably easy and not so much of a challenge, you kind of really we got a really big push, and we kind of, learned stuff that, as I was like 14, 15 at the time, and I didn't kind of see that stuff again until university. So it kind of really pushed us, and, which kind of built our confidence and our ability to solve problems and to kind of work hard and kind of get through things. So some of his methods were a bit questionable, but it kind of was quite a formative experience. And say when I did my PhD, I kind of turned into a bit of an academic orphan, because my supervisor left just as I was, actually before I turned up. So I kind of got accepted to do the PhD, and then my supervisor left, and then I kind of turned up. So I was kind of adrift a bit, and then I got had actually ended up with three main supervisors: Jenny Gilbert, Harry Pinkerton, and Steve Lane. And Steve did really the bulk of the hands-on supervising, and really helped me a lot, kind of building the experimental equipment and talking through the results and that sort of stuff. So that was really great. But we also had in my group, we had another PhD student, Mike James, and he was like, I think, a couple of years ahead of me, and he really kind of helped me a lot. It was really kind of modeled for me, what being a good scientist was about, and he gave me lots of practical help. Even though I was kind of, a bit kind of naive at the time, and kind of really gave me, tons of help, and like help kind of building equipment and all sorts of stuff like that. So that was great. I mentioned Jill Jill Jolly, who was the director of the MVO when I first started, and she kind of offered me my first position here.
Mm-hmm.
So, and she was really, good leader, and kind of showed kind of what it was to be, a good leader, but kind of keeping calm under pressure and that sort of stuff. So that was great. So I mentioned Peter Mallon, and again, that was really a really great opportunity that he afforded me. And he's kind of one of those people who kind of, he said, oh, you're smart, you can figure it out. So a lot of stuff, you're just going to completely thrown into the deep end. So it's like, here's the MT equipment, you go to Montserrat, figure it out. and yeah, and so that was, you kind of develop a lot as a person in those kinds of circumstances, and that, having that, he has that kind of level of trust in your abilities. Whereas, so we'd often, so kind of feel a bit like kind of geophysical special forces. So we do these projects in different places, and be like one or two of us would go, and we'd be gone for like a month, 2 months, 3 months, and you have minimal contact. You just have a certain amount of money, the equipment, and you just figure it out. and kind of make the project work. And things go wrong all the time, and you just, okay, how do I solve this problem? What do I need to do here? And so that kind of was quite a kind of formative experience at the time, based in New Zealand. But so we would do, go to Chile, and we would have to have people to help actually do the physical work, because we'd be digging a lot of holes to put equipment. So you have, we'd have a team of Chileans who are helping that. So you kind of, having to try and learn enough Spanish to kind of make communication possible, and kind of navigating all of that. So it was a good experience. A lot of stressful times, but it was good, and we did a lot of interesting work. And so like when I came back to Trinidad, the director at the time was Dr. Richie Robertson, and again, he was another really good leader who kind of modeled good leadership, and you always felt that he kind of supported to kind of develop your interests, and do interesting things, and kind of do as much as you can, and also kind of trying to build like a good team spirit, and kind of build that kind of so it's really good. So I mean, when I floated the idea of applying for the directorship, he was really supportive. I was like, I was very kind of tentative. I was like, I don't know if I'm kind of up to this, but yeah, he was very supportive. So yeah, I've had a lot of, I've worked with a lot of great people. I've worked in different places and different times, and I've always had the luck to work with lots of really great people, and kind of to work in areas where everybody believes in what they're doing. I think it's something useful and important, and that really helps a lot. That you kind of have that, and everybody has that kind of belief that what they're doing is useful.
Yep.
So yeah, so I think that's me.
Great message, and I appreciate that. One final question, going back to the very beginning of the episode, when we first introduced you, and you brought up the professor on Gilligan's Island. I just have to ask, your top line thought, why the hell couldn't he fix the boat? He was that smart.
Yeah, well, he knew that, he wouldn't, the series would be over and he wouldn't get all his residuals.
Exactly. Well, Dr. Wright, it's been a real pleasure having you, listening to your journey and sort of everything you're going to be doing moving forward in this evolving field, evolving specialty. For everybody that's going to be watching this episode or listening on the podcast, you've been listening to Dr. Graham Ryan, director at the Montserrat Volcano Observatory on the island of Montserrat in the West Indies. Dr. Wright, thank you for taking so much time out of your very busy schedule to talk to us and educate us on this topic. And thank you for everything you do in generating knowledge and protecting the future and what's potentially is coming. So thank you for it. Was a really great discussion.
Thanks a lot, Ira. It was an interesting conversation. Thanks.